Hello, this is Jack Jackson. In this video, we're going to talk about another type of transformation that are called horizontal and vertical strains. On a coordinate grid, it's fairly straightforward to perform size changes, that's expansions and compressions, both vertically and horizontally, independent of each other. Multiplying only one coordinate by a constant is a type of transformation is called a strain. If the expansion or compression factor is the same vertically and horizontally, then the transformation is actually a dilation about the origin, which is a similarity size transformation. However, if these changes are not by the same factor vertically and horizontally, the resulted image is not similar to the original pre-image, although a strain is a linear transformation. Neither proportionality of lengths nor equality of angle measures are preserved by strains. So they're pretty straightforward when you're looking at formulas. So let's look at a horizontal strain first. First of all, we're given any relation in x and y. If we replace x by x divided by some constant, positive constant, then the graph is expanded or compressed horizontally, a horizontal strain, by a factor of c. If c is bigger than 1, then we have an expansion. If c is less than 1, we have a compression. Of course, if c equals 1, then it's just the identity function. So let's illustrate this with an example here. Let's start with y equals x squared. So here I've just picked up some of the usual suspects, the integers from -4 to 4, put in a table of x's, use the formula to say that we square the x's to get the y's to obtain the corresponding y values. So this is a portion of the table for this particular original relation. It's actually a parabola or a quadratic relation there. Now, what we're going to do here is replace x by 2x. Now, it is typically what happens is that the formula is backwards from the graph. What you do in the formula has to be backwards from what's actually occurring in the graph. So when we replace x by 2x, notice that happens inside. You put a parentheses where the x is. In place of x, you put 2x. Notice that that is going to be a change in the x, so the y side is left alone. So if we want to line these up as pre-image to image points, notice that the y's are staying the same. So actually I just copied this column and pasted it over here. Now, what happens to the x values? Well, if you replace x by 2x, what you're really doing is dividing the x values by 2. So -4 divided by 2 is -2. -3 divided by 2 is -1.5. -2 divided by 2 is -1, and so forth. Okay, and so this gives us our images. Notice that this does work. If I put -2 in here and multiply by 2, I'm back to -4, then square it, I'm back to 16, which is the appropriate output. Let's try another one. 2 times 1 is 2, squared is 4. 1.5 times 2 is 3, squared is 9, and so forth. Now, what's that going to do to the graph? Well, every point on this graph is going to have the same y value on both graphs, but the x values are going to be changed. And if you notice, they're brought closer to the y-axis. The ones that are on the y-axis are left alone by this horizontal strain. So the origin point stayed the same, or any point that would have an x-coordinate of 0 would stay the same. But the y-coordinates are brought in. So for example, if we take the point 2, 4, which is right there on the original, it's brought in to its image, which is right here, the point 1, 4. So 2, 4 is replaced by 1, 4. And notice that that's brought halfway closer to the y-axis, halfway closer to x equals 0. Okay, and that happens all the way up and down this thing. So what's happening is now this graph is now the same height, but it is now half as wide. If this was stopped at some point, like say if it didn't go beyond, say if it didn't go beyond 416, then this one would also not go above 16 on the y's, but it would be half as wide. Okay, how about another example? Y equals x cubed. Again, I take some standard examples here for x's. Could have picked anything. I picked those. Cube them to get these here. Negative 4 cubed is negative 64. Negative 3 cubed is negative 27. 2 cubed is 8, and so forth. I want to multiply the y values by the x values by 3. So notice once again the y values here are the same as the y values here. If we match up a point to its pre-image point to its image point, the y values are the same. But the x we've been multiplying by 3. Negative 4 times 3 is negative 12. Negative 3 times 3 is negative 9. Well, this is going to make it 3 times as wide. Now, if you're going to multiply the x values by 3, what you do in the formula is divide the x by 3. In other words, replace x by x divided by 3. Remember, the formula is backwards in these transformations. And what do we see here? The original graph is this one right here, this basic cubic power function. Okay, the point at the origin is fixed, but all the other points are moved 3 times as far away from the y-axis. So this point at 1, 1 is now over here at 3, 1. And the point at 2, 8, right up here, is now at 6, 8, and so forth. So points on the right side of the axis get moved further to the right. Points on the left side get moved further to the left. So this one might call this expanded or stretched horizontally, whereas this one over here was compressed or squished horizontally. Remember, the x is the horizontal variable, so this is a horizontal strain. We can also do vertical strains by doing the same thing to the y instead. So again, I took the same example, y equals x squared, got our same table here, but this time when we're lining them up, the x's will be left alone from pre-image to image point. So the x's here are the same as the corresponding ones here. If we replace y by y divided by 2, what we really do is multiply all the y values by 2. Okay, and so we take the y's and multiply by 2. 16 times 2 is 32, 9 times 2 is 18, 4 times 2 is 8, and so forth. What we're doing in the formula is replacing y by y divided by 2. I prefer looking at it in this form right here because more clearly you can see that the x side has been left alone. Nothing has changed there, but y has been replaced by y over 2. Now if you solve for y, it's y equals 2x squared, which you have to do in some calculators. And so for, like, if you want to put that on TI-84, for example, you might want to solve for y. But either way, you get the same formula here. So for example, if we work this out, 32 divided by 2 is 16. Negative 4 quantity squared is 16 as well. So that one works. So what's going to happen to the graph? Well, it's twice as tall. All points are twice as far from the x-axis. Anything on the x-axis would stay right where it is, for example, the origin. But this point that was at 1, 1 now is at 1, 2. The point that was at 2, 4 is now at 2, 8, twice as tall. Okay, so this is taller here. If it stopped at 416, at negative 4, if it was only defined from negative 4 to 4, then this one over here would still be only defined from negative 4 to 4. It wouldn't be any narrower, or it'd be the same width overall, but it would end up being taller. Okay, over here we have another example, y equals x cubed. Once again, we have a basic table of that. Replace y by 3y, which you can see we did there. So what are we really doing? We're leaving the x's alone, and we're dividing the y's by 3. I've done them in decimals, repeating decimal form here. So the graph then turns out to be 1/3 as tall. All points are 1/3 as far from the x-axis. So this one got squished, compressed vertically, whereas this one over here is stretched vertically. Now, if x is replaced by x divided by c and y is replaced by y divided by c, the same constant on both variables, So you got the same amount of compression or expansion in both the x and the y direction. Then the image is actually a dilation by a factor of c about the origin. So in this example, we can start with the unit square, x squared plus y squared equals 1, and we replace it by x over 4 squared plus y over 4 squared, and it's expanded by a factor of 4 to now have a circle centered at the origin, but of radius 4, not radius 1 like the original. So here are a couple exercises you could try. Transform the unit circle by dilating about the origin by a factor of 4. Actually, that's what that one actually is right there. Let's do another factor. Let's do a factor of 5. Graph the pre-image and the image on the same grid using GeoGebra. Give the formula for each relation. Another exercise, using separate strains of vertical and horizontal translations, show how to obtain the general form of ellipse as a transformation of the unit circle. Next exercise, illustrate this result by applying a horizontal strain of factor 4 centered at the origin and a vertical strain of factor 3 also centered at the origin to the unit circle. Follow this by translation by the vector 2, negative 3. What's the formula for the resulting relation? Graph the final image in GeoGebra. That's going to be a ellipse. All right, I think we'll stop here and summarize a lot of these things in the next video.